this video, we're going to look at velocity-dependent forces. That is, what happens if the force acting on an object depends on how fast the object is going. Now, this is actually a little bit more of an advanced topic, but it's an important one, so I wanted to at least show you how these kinds of things are considered and tackled in principle. Now, one of the more common examples of a velocity-dependent force is the force of air resistance or fluid resistance. Now, if we think about regular friction, the force of sliding friction, it does not depend on the velocity. It's independent of the velocity. But there are resistive forces like air resistance or the resistance of something passing through a liquid. And those forces actually do depend on the object as it's going through that fluid. And by the way, the term fluid is a generic term used in physics to describe either a gas or a liquid. So either of those are considered fluids. And both gases and liquids, i.e. fluids, can create velocity-dependent forces on objects that are passing through them. Now, for small objects that are moving at relatively low velocities, the force of resistance, which we call the drag force can often be approximated as being proportional to the velocity. That is, if I double the velocity, the drag force is doubled. If I triple the velocity, the drag force is tripled. And for lots of situations, it turns out that that is the nature of the force of air resistance. And for objects moving at higher speeds, the drag forces can often be approximated as being proportional to the velocity squared. So that creates an even more pronounced effect. As the velocity goes up, the force goes up by the square of the velocity. And so in this video, we're actually going to look at the former case. The force is proportional to the velocity. And so the drag force is proportional to the velocity. How does that affect the motion? So we're going to just look at a very simple case to illustrate some of these ideas. And we're going to look at the case of an object dropped and falling under the influence of gravity in a resistive medium like air. And so I've got a ball, I drop it, and as it falls, the air resistance is going to affect its motion. And we want to know, how does it affect the motion? So first of all, I have my ball here, and I've got my coordinate system, and I'm decided to make the y direction positive going downward. I've lined my coordinate system up with the acceleration, and so that, remember, we can tilt or turn our coordinate system anywhere we want, and that's just how I've chosen to do that today. And so we have the weight is pulling the ball down, and there's going to be a drag force which is in the opposite direction. And just like friction, the drag forces here are going to be in the opposite direction to the motion. So this guy's falling down, the drag force is going to be in the opposite direction to that. Now, we've also said that the drag force is proportional to the velocity. And so I can actually write that as an equation. I can say the drag force is going to be minus b times the velocity v. And this b is just a constant, and that's what it means for something to be proportional. It means you multiply it by a constant. Now, can you guess why I put a minus sign here? I hope you recognize that that means that the force here is going to be in the opposite direction to the velocity. That minus sign gives us that relationship that the velocity and the drag force must be in opposite directions. Now this b, it depends on the nature of the fluid that this thing is passing through. It would be different, say, for water than it would be for air. The other thing it depends on is the shape of the object passing through, how much surface area is impacting the air as it passes through it. Typically, the more area that is catching the air, the bigger the resistive force is going to be. So now I can apply my Newton's second law. I can say the sum of the forces in the y direction are going to be the weight, mg, and it's positive, again, because I've set my coordinate system pointing downward, minus b times v, because the resistive drag forces are in the negative direction, and that's going to be equal to m times a. So I have the sum of the forces equals to m times a. Now, notice I've written my acceleration in terms of its definition, the derivative of velocity with respect to time. That's my acceleration here. Why did I write it like that? Because I know that I want to solve for the velocity of this thing as it's moving. And so I'm writing everything that depends on v in terms of v, and now I have a first order differential equation. It's first order because it has a first derivative in it. And this equation is going to allow us to solve for the velocity of this falling object as a function of time. Now, before we do that, before we actually solve the differential equation, we can look at the physics and just kind of understand what's happening physically in this system. So this guy is dropped from rest. And so at t equals to 0, it has an initial velocity of 0. And so if I look at my sum of my forces here, I get this term is 0 and mg is equal to m times a at the very beginning. In other words, it starts out with a equal to g. It's got an acceleration equal to g once it's released. And so it's going to start going faster and faster. As v increases, it's no longer 0, it's going faster and faster. The drag force is going to get bigger and bigger. And so what you have is the force, it starts out as mg, the weight, but as it speeds up, the force gets smaller and smaller because I'm subtracting this drag force term, and this drag force term is getting bigger and bigger. Eventually, this guy is going to be as big as this guy, and when you subtract them, you'll get 0. What does that mean? It doesn't mean that the object stops. It does not mean that the object slows down. So what does it mean that this term is equal to 0? What it means is that it stops accelerating. Its velocity stops changing. And so what we're going to see is that the velocity is going to get bigger and bigger and bigger, but the rate at which it's getting bigger is going to slow down. And eventually, it's going to stop getting bigger, and you'll reach the final velocity, which is constant. And that final constant velocity is known as the terminal velocity. Now, when the object has reached its terminal velocity, we know the resistive force is equal to the weight. In other words, mg is equal to b times v. But that only happens when the velocity is the terminal velocity, so I've put a little t here to let you know this is the terminal velocity that I'm talking about. When I have this relationship, I can solve for the terminal velocity, and I find that it's got to be mg divided by that parameter b. By the way, what would the units for this parameter b be? Pause the video for a minute. I want you to just pause the video and figure that out. Go ahead. I'll wait for you to pause the video, and hopefully you're back. Hopefully you did that and you now know what the units of b are. In any case, this whole term here, that's the final velocity that this guy's going to have, and it's the terminal velocity, and it happens when it's going fast enough so that the resistive force equals the weight. Now we can actually solve for the velocity as a function of time by solving this differential equation. So we're going to determine the velocity of the object dropped from rest, subjected to air resistance, that is proportional to the velocity. This is what we're going to end up with. And so I have my sum of the forces here in the y direction. That's mg minus bv is equal to m dv dt. I want to solve this guy for the acceleration, dv over dt, so I'm just going to divide every term by an m. So I'll cancel these m's and I'll have a b over m here. What I end up with is that the acceleration is equal to little g minus b over m times the velocity. And now what I want is I want to solve this equation for v. How do I do that? Well, we're going to use the same technique that we've used previously when we've encountered first-order linear differential equations. Let me remind you of when we solved for the kinematics equations. we said that the acceleration is equal to dv over dt. And we said we can solve for v by separating the variables. I'm going to move this dt over on this side. I get a dt is equal to dv. And now I want to solve for v, so I have to integrate that guy. And if I do it to the right side of the equation, I have to do it to the left side of the equation. And I did those integrals, and we plugged in initial conditions and did all that stuff, and we derived our kinematics equations. And we did it by using this separation of variables technique. That's exactly what we're going to do here. I've got this term that involves v and this term that involves v. I want to move all of these over to one side, and then I'll move the dt terms over to the other side. So that's going to be our approach for solving this equation for v. So here's what I have so far. I've got dv over dt is equal to g minus b over m times v. Now I'm going to simplify this a little bit. I'm going to factor out a g. Now there's no g in this term, but I can put one in it. If I have g over g, that's essentially 1, right? G over g equals 1. If I write a g over g on this term, I can factor the g's out, and I end up with the acceleration is equal to little g times 1 minus bv over mg. And you'll see why I did it this way in a minute. Basically, doing this little math trick is going to make my algebra a little bit easier to deal with. So I want to separate the variables and get all the v terms on one side and all the t terms on the other. Now this thing in the parentheses here, 1 minus bv over mg, that entire thing, I can't just separate out the 1. That's an entire term involving v. So I'm going to divide both sides by the thing in brackets, and I'm going to get dv over here on the left divided by that thing in the parentheses there, and then I'm going to take my dt and move it over to the other side, and I'm going to then integrate both sides. And so I end up with dv over 1 minus bv over mg is equal to g times dt. And I've gone ahead and put my integrals. I'm going to integrate both sides. This g is constant, so I can pull it out front. And what I have is this crazy-looking integral and this simple-looking integral. We know the integral of dt is just t, but I have to figure out how to do this crazy integral to solve the problem. Now, before I do that, let me look at my limits, because I've gone ahead and put them in. I know that I'm starting from rest, so the initial velocity is 0, and the final velocity I'm just calling v. If I were being really careful, I should probably call this v sub f or something like that, but I'm going to be a little bit careless and just call that v. And the time, of course, is integrating from some initial time equal to 0 to some final time t. And now I can do both of these integrals. Obviously, the integral on the right is just going to give me g times t. But how am I going to do this integral on the left here? This looks very much like the integral of 1 over 1 minus x dx. And so how do I do that? Well, that's just the natural log. I would have the natural log of 1 minus x, but then, because of this chain rule thing, I'm going to have a minus sign that comes out front, and so I would need to have this be minus, and that's what this integral would give me. And so this integral over here on the left, it looks very much like that. I've got 1 over 1 minus x, except I've got this thing times the x, this bmg, b over mg. And so when I do my chain rule type thing, I'm going to have this b over mg come out as well. But of course, I have to have that upside down so that it cancels. And so I can recognize that this integral looks like the natural log of 1 minus this thing times this factor out front. And that's going to go from v equals 0 to v equals to some final v. And so I've got my limits here. And so all of this craziness has to equal to g times t. Now, I can immediately see one thing that's going to let me simplify this. And this is why I pulled this g out here. Because my natural log is 1 minus this term. What happens when I plug in this 0 here? I get 1 minus 0, which is the natural log of 1. Does anybody know what the natural log of 1 is? If you plug it into your calculator, you'll find that that's equal to 0. And so by doing this weird factoring up here, I just made my life a little bit easier. So when I plug in this limit, this term goes to 0. And then I plug in my v final here, and it's just going to be the v here. And so that's what I'm going to do. I also noticed, just real quick, there's a g on this side and there's a g on that side. So I can cancel those, and that'll just make my life a little bit easier. So when I cancel those g's, this is what I end up with. I get minus m over b, natural log of 1 minus bv over mg is equal to t. And I want to solve this for v. So I've got to get rid of this natural log. So I'm going to move this minus m over b to the other side, and I've got the natural log of the stuff in the parentheses is equal to minus b over mt. And now I can take the inverse of the natural log to get rid of that ln. What's the inverse of the natural log? It's the exponential function, e to the x. And so if I take e to the both sides, I get e to the natural log of this stuff, which kills the natural log, and I'm left with the stuff in parentheses is equal to e to the minus b over m times t. Now I can solve this guy for v. I'm going to move this 1 to the other side, and then I'm going to multiply by minus mg over b to get rid of that term, and that'll let me get v by itself. When I do that, when I solve for v, I find that the velocity of my ball is going to be mg divided by b times 1 minus e to the minus b over m times t. And that is the velocity of this ball at any time t. Now let's examine this formula, and we can check against some limiting cases that we know. The first one we can look at is t equals to 0. Now, what's going to happen when I plug t equals to 0? And remember, this t is in this exponential. So it's e to the minus b over mt. That's the power of this exponential function. What happens when I plug 0 here? What is anything to the 0 power? It's just 1. So if I plug in t equals to 0 here, I get v is equal to this stuff times 1 minus 1. In other words, what we find is that the velocity is equal to 0 at t equals to 0. And that is exactly what we said it had to be. As if we said that it was dropped from rest, that means that the velocity was initially 0. Now, what about another limiting case? Let's let t go to infinity. And so what is going to happen if I plug in the limit as t goes to infinity right here? Well, let's look at this e to the minus b over m times t. If I write that out, e to the minus x is equal to 1 over e to the x. And so this guy, as x gets bigger, this whole thing gets smaller. It's the same thing here. I have e to the minus b over m times t. As t gets bigger, this whole term gets smaller and eventually goes to 0. And so what I end up with is that the velocity is mg over b times 1. And I can write that down, that the velocity is equal to mg over b. But that's exactly what we figured out the terminal velocity has to be. And so as the time gets bigger and bigger, the velocity approaches the terminal velocity. These are what we would expect for these two cases. And so that lets me feel a little bit more confident that my formula is actually correct. It's worth noting that we can actually plot this function of velocity as a function of time. And so the velocity starts out and it's increasing. And you know that if I have a velocity versus time curve, what's the slope of a velocity versus time curve? Do you remember? The slope of a velocity versus time curve is an acceleration. And you can see here that the slope starts out big, but then the slope is decreasing, and eventually the slope gets to 0. And it gets to 0 asymptotically with the terminal velocity. And so this is the behavior of the velocity of the object as it falls. It starts out with a bigger acceleration, but the acceleration is decreasing, and eventually it goes to 0. And at that point, it's reached the terminal velocity. There's a lot of really great physics in this video, and I hope everyone appreciates just how cool some of this stuff is. In any case, we're at the end of the video. We'll move on to the next one, and we'll keep going.